Hello, my name is Thomas Cook and my project focuses on high entropy alloys as catalyst technology. My project is important due to 96% of hydrogen being produced globally being produced through steam reformation. So steam reformation is transformation of coal or natural gas into hydrogen. This hydrogen can then be used as an energy storage medium. However, it is not a renewable resource due to being made from fossil fuels. The other main way of producing hydrogen is through renewable energy. So that is, you use electricity to transform water through electrolysis into hydrogen and oxygen. This is the hydrogen evolution reaction and the oxygen evolution reaction. This method is mainly not used due to the expensiveness of the catalysts, which are normally from the platinum group. This makes it many times more expensive than using steam reformation. However, there has been research conducted into high entropy alloys as catalysts for this hydrogen evolution reaction and oxygen evolution reaction. This has shown promise. The aim of my project was to be able to produce a high entropy alloy that could be successfully used as a catalyst for the hydrogen evolution reaction. Ideally, this catalyst would have catalytic abilities similar to those of platinum group catalysts and would eventually be able to replace them. The composition of the high entropy alloys was selected based off thermodynamic equations to determine which combinations would be able to form high entropy alloys, as well as selecting elements that were performed well as catalysts for the hydrogen evolution reaction. The compositions selected were aluminium, copper, iron, molybdenum, and nickel, and chromium, copper, iron, molybdenum, and nickel. The main difference between these two combinations is that one contains aluminium, the other contains chromium. The other four elements are kept the same between each of these compositions. An equimolar composition was selected for both. The high entropy alloys were produced through high energy mechanical milling. This involves having powders and small ball bearings in a vial that is then rotated at high speeds in a planetary mill. The powders will collide with the ball bearings, which will break them apart and force them to combine and react with other powders so that coherent alloys could be formed of small particle sizes. The pure powders were milled in a planetary mill at 350 rpm under an argon atmosphere to prevent excess oxidation that could have been dangerous. Stainless steel ball bearings as well as vials were used, and a ball to powder ratio of 10:1 was maintained. The samples were milled for 5 hours, 10 hours, 20 hours, and 30 hours. This would allow us to see at what time the high entropy alloys were formed, and therefore had the smallest amount of time possible to forming these high entropy alloys. To determine if the high energy mechanical milling had formed a high entropy alloy, that milled powders were analysed through XRD analysis. The produced XRD spectrum would have the peaks indexed to determine what phases were present in the sample. For the formation of a high entropy alloy, there would ideally be a single phase that had formed. This desired phase would be an FCC phase, as this phase has been found to be the best for catalysts to facilitate a hydrogen evolution reaction. The XRD spectrum shown here is for an aluminium, copper, iron, molybdenum, nickel high entropy alloy sample that had been milled for 20 hours. From the peaks present, it can be determined that at least two phases had formed, that these peaks indicate that at least a BCC and an FCC phase had formed. Most of the peaks present correlated to reference peaks of elemental molybdenum and copper, with the peaks of the BCC phase corresponding to the peaks found for molybdenum, and the peaks for the FCC phase corresponding to those of copper. As copper and molybdenum were so identifiable, this suggests that they do not react with the other powders to form a high entropy alloy during milling. A high entropy alloy therefore did not form with 20 hours of milling, and a longer milling time would be required. A 30-hour sample has been milled for this combination, but is yet to be analysed through XRD analysis. Much of the work has yet been completed for this honours project. Further work that still needs to be completed includes XRD analysis of an aluminium high entropy alloy composition being milled for 30 hours and XRD analysis of a chromium high entropy alloy samples. Additionally, the shortest possible time for vacuum sintering to produce a solid piece that can be used for electrocatalytic testing needs to be determined, as well as determining particle morphology. To show catalytic testing of the high entropy alloys needs to occur, this will focus primarily on mass activity and over potential of the samples for a hydrogen evolution reaction, as these catalytic properties are easily comparable to other materials used as catalysts, and due to time constraints, testing based on lifespan and degradation is not possible.